Hello, I'm Mike. I work for IBM Research, and I'm going to talk about using restricted address spaces in the Linux kernel for purpose of container security. From the old idea of chroot that developed in the late 70s for Unix systems, now we see that containers really caught up. They are hype. They're everywhere. They are used in private data centers. They're used in public clouds, and they power very much of modern applications. However, despite being in isolation primitive, containers often run inside virtual machines. Like every public cloud doesn't allow you to execute containers on the bare metal. You need to purchase a VM and then you can run containers inside it. A major reason for that is that because containers are perceived less secure than virtual machines, and despite their convenience for everybody, still most of container users pay the price of double virtualization for container environments. So we've asked ourselves if this is really necessary. Can we somehow improve container security so they will be at least as secure as VMs or probably even more? Usual argument for proponents of VM being more secure is that VMs are protected by hardware. Since container run as a normal process on steroids in the Linux system, the hardware we have that can be used to protect the containers is a memory management unit, and the memory protection and address space isolation has been the best protection method since the invention of virtual memory. It protects every process from each other. It protects virtual machines from each other in a slightly different way, but still it exists there. What we are looking for is how can we use memory management unit to prevent damage in the bare metal container system, in the bare metal container host, so that if there is a malicious tenant, it will be at least limited to its own environment and won't be able to use to introspect memory of other containers. And we are working on creation of restricted address spaces inside the Linux kernel in the privileged mode to facilitate that. As you all know, containers run on the shared Linux kernel, which is a large attack surface, and while we are looking to isolate parts of Linux kernel from itself to reduce the attack surface, we've been thinking that since containers use namespaces for basic isolation primitives, probably we can extend the namespace mechanisms to include address spaces as well, so that we'll be able to create an address space for a Linux namespace. I'll extend about it a bit later. There is several projects that do similar things. First of all, there is page table isolation that came as a mitigation for meltdown vulnerability in CPUs that allows any user to actually introspect memory of the entire system. What Linux kernel did for the mitigation, they started to split kernel page tables and user page tables, and once the mitigation is enabled, user space applications do not have mappings of the kernel memory as it was previously before the meltdown. There is also work in several places that aims to improve mitigation of various speculation vulnerabilities in the processors. First, it's work that is done by Oracle Linux team. They are doing KVM address space isolation, and they try to create a restricted context for execution of VM exits for KVM virtual machines. And there was a proposal from Amazon development team about process local memory that creates kernel memory areas that are visible only in a particular context. Usually it's a context of a virtual machine, but it can be in general any process that runs on the system. And as far as I know, Amazon work doesn't continue this day. At least they do not show any signs of it upstream. And Oracle have sent several patches for KVM-ASA, how they call it, and I think they target the inclusion to the mainline of this work. So we've started to think how can we restrict the attack surface and what can we do to use MMU to protect tenants from each other. And the first prototype we've done was called system call isolation, that actually based on the idea that since system calls is the attack surface for the container environments, we want to execute part of the code inside the system call in a restricted address space. So with the system call that runs in very limited mappings of the kernel, we can get a page fault whenever there is an access to some additional memory, and we can try to verify if this access is secure and allowed, or if it's a malicious jump that should be prevented and the application that performed it should be killed. We posted an RFC for this mechanism that presented ROP attack prevention with is a restricted address space in the system call execution, but it has some weaknesses, like it cannot verify return targets, which is the most important thing that should be done for ROP attack prevention. It doesn't work very fast, and it provides only page level granularity for the introspection of possible malicious successes. So if anybody, even an attacker, calls the same function twice with wrong parameters, so it will return immediately, and then with the intended, and then it can use the intended gadget to continue his attack. Now, Intel announced a CT technology that makes the whole software emulation irrelevant. There are still no chips with this available on the market, but apparently they will appear there at some point in the time. We've thought about follow-up possibility to use simpler mechanism to construct shadow stack and to verify red target, but we didn't continue this work, at least at the moment. Next thing we're trying to do, and we are actively pushing for it into the mainline, is to create secret memory areas for in the user space part of the page tables, and make these areas invisible in the kernel, so that even if the intruder has control of the has ability to read the memory from the direct map, the area that is mapped in the user space is not mapped in the kernel direct map, and thus nothing in kernel can access this memory. The idea is that these such areas can be used to store secrets like encryption keys and so on. Or on the extreme side, such areas can be used to protect the entire virtual machine memory without enabling encryption technologies like SEV. The first attempt we did was an extension to memory map, a new flag that we called map exclusive, so that the memory mapping done with this flag is excluded from the direct map. It is not seen by the rest of the kernel. So the user can do something like mmap. Of course, there should be a check for the result of mmap. And then a user can define an IOVEC and use that IOVEC to read the secret key and store the secret key in a secret area of memory. We've got quite a feedback about this submission. You can read it on the link below. So advantages of using mmap is more convenient interface. Normal for memory management, and it was a simple implementation in the first glance, but probably we missed several points, and the drawbacks that implementing new mmap requires new VMA flag, and more importantly, we required a new page flag for struct page, and these are very scarce resource. For 32 bits, there are no more free flags anymore, and there are restrictions on how many page flags can be on the 64-bit systems as well. Now, since we are using page flags and VMA flags, we should do extensive audit of the entire memory management subsystem to see if there is any code that tries to access that secret VMA and should be told not to do that. And there was a major concern raised by the community that creating such special memory areas will cause a fragmentation of the direct map, and instead of being covered with 1 GB and 2 MB pages, at least on x86, the direct map will be split into a lot of 4K pages, which will cause performance degradation for the entire system lifetime. Then we went ahead for the next version, and taking into account the problems with the direct memory mapping, we implemented a new extension to memfd create system call that allows a user to create a file descriptor that can later be mem-mapped as a normal file with some protection flags. And the usage would be a user creates a mfd create, it passes mfd secret flag. Then the user specifies what kind of protection they want, and at last the user calls mmap and passes the file descriptor obtained from the previous system call, and then mmap creates a memory area that again is secret. It's hidden from the rest of the kernel, and a privileged code has no access to it. The advantage of using a file descriptor backed memory is that the whole decision making about how to access this memory can be hidden behind the mmap and fold methods that we can override inside the secret memory implementation. It is possible to use pre-allocated memory to reduce fragmentation of the direct map. At that point, we didn't implement it yet. There are still some places in the memory management subsystems that might need to be changed to avoid rogue accesses to the VMAs that created by memfd create secret. It could There was some more complexities in the implementation of a simple mmap interface, and still there is a concern about fragmentation of the direct map. At some point, we've got curious about how direct map fragmentation actually affects performance of the system. So we've run a couple of benchmarks on a system that used large pages, very large pages, and normal pages in the entire direct map. So the blue bars are for the runs with the direct map mapped with 1 gigapages. The red bars are for direct map covered with 2 meg pages, and the green ones are for 4K pages. We've run several benchmarks from Phoronix test suite, namely FSMark, PGBench, Redis, Apache, and Kernel build. And these charts represent benchmarks that run from SSD, and these two charts represent benchmarks that run from TempFS. And we've done 2 variants for each one with mitigations on and one with mitigations off. The numbers shown are relative degradation, with the base being 4K mappings in the direct map. As you see, there is no straight cut winner for any of the configurations, and it's not necessarily huge pages perform better or significantly better than 4K pages, and for sure this is very much depend on the workload. Now the last thing we've done is we created a last version of the patches we've sent is the new system call dedicated for creation of secret memory areas. It's we've called it memfd secret. It also provides an ability to create file descriptor like the extension for memfd create we've done previously. Its implementation is a bit secret, is a bit simpler than previously. We've also added some pooling of large pages to decrease fragmentation of the direct map. We've implemented the ability to pre-allocate large memory pool at boot time, so that if the user would want to manage its memory in the secret memory in the user space, they'll be able to do so simply by pre-allocating large memory pool at the boot time and then using it for whatever purpose they want. We've sent the patch just a couple of days ago, and as of now we already got 2 ACKs. And now for the upcoming projects, for our vision how we are going to protect namespaces with a page table. We have some mostly working prototypes that crash from time to time, so this is more of a hand waving part of the presentation than the actual things. But anyway, what we think is that since namespaces is a basic primitive for container isolation in Linux, and they anyway create objects that are private to the particular namespace, there is no reason that the rest of the operating system will see and map the private object of a namespaces. So we think that we can implement, and we actually implemented this for NetNS, we can implement per namespace page tables to improve isolation of the Linux containers. The page tables will be shared by all the processes belonging to the same namespace, and on the other hand, the mappings of private objects in these namespaces will be seen exclusively by the namespaces that own them, which means only the processes that run in certain namespace will see some of these objects, and the rest of the privileged code will not have these objects mapped. So we've started our implementation with network namespace. As you know, just a brief reminder, network namespace implements an entirely independent network stack with the virtual or physical devices, TCP and IP caches, IP tables, everything is entirely independent of the other network stacks implemented in the system. For the most parts, objects inside the network namespace are private to that namespace and should not be accessed by any other part of the operating system, like a TCP cache of namespace A. It should not be visible for default namespace and for namespace B. The same applies for IP tables, for flow caches, for outing tables. Whatever is allocated by the network stack is private to that network stack. The only exception is the SKB objects that represent network packets. So for most configurations of virtual networks in container environments, packets do cross boundaries of the namespaces. They do cross boundaries of the containers. Packets are sent from container to the host, from host to the container, from one container to another. So SKBs cross namespace boundaries, and these objects need to be mapped in several namespaces, probably one at a time, but at some point the mapping should be adjusted for SKB when it crosses the namespace boundary. During one of the discussions about actually KVM ASI, Thomas Glexner summarized very well what is required for restricted address spaces framework. It's basically 2.5 steps. And the first one is the ability to create the restricted address space from the existing mapping or from scratch. Like there should be a mechanism to tell the kernel, okay, here these are pages that I want mapped exclusively here, and these are mapped everywhere. And the page tables should be able to coexist safely. Next 2 points are about how to make the context switch between the normal kernel state and the restricted kernel state. So there should be a way to enter restricted mapping and exit the restricted mapping, and there should be some kind of state machines that keeps track on the state. We are primarily focusing on the first part, is the creation of the framework for restricted mappings. What we consider needs to be done is that currently there is no first-class abstraction for page table in the Linux kernel, and we'd like to create one. Up till now, most of the kernel memory management was dealing with the user space memory, and therefore it is an assumption, implicit assumption all over, that struct struct is a page table. We would like to introduce new struct page table to represent a page table proper, and then structs will be able to reference this page table, and there will be several independent page table with restricted mappings inside the kernel itself, and these will be additional kernel page tables, unlike today when we have only init which is the kernel page table. We need some mechanism to clone and populate restricted page table. For example, we can start from the existing mappings that kernel creates for the entire physical memory, and then we can cut some pieces from these mappings. Or on the contrary, we can start from an empty page table and only add the necessary parts into that page table as the subsystem that manages the restricted namespace restricted page table requires. So there should be functionality to drop mappings from the page table and to map pages to this page table. And the most difficult part from the page table management is the tear down of the page tables. there is strict requirements from TLBs, so that page table will be managed in very particular way. First, the page table should be unmapped from the higher level. Then we should update the TLBs, and only then the page table can be freed. This whole process creates quite of a complexity, especially when some part of the page table are shared with other page tables. The context that will use restricted page table and will create restricted page table. First of all, there is also already PTI that does this at boot time, and we are planning to switch PTI to use our new page table objects. The page table could be created when we create a new process or entering a new namespace, so that whenever a user calls clone, fork, or whatever, we need to create a restricted page table for that particular call, we should be able to do so. The same applies for entering and leaving namespaces, so that when a user calls unshare or set an S, there should be an ability to create a page table that's local to that namespace and that guards the namespace objects from the other namespaces. And for the KVM ASI project, the point of kernel context creation is vCPU create or VM create, depending on the particular page table and particular restrictions that they want to put in the restricted mappings. The context switch is for restricted memory mappings could be implicit, like it could be explicit, like system call boundary for PTI or VM enter exit for KVM ASI, and there are also implicit transition like context switch that scheduler does unrelated to the management of the restricted address spaces. There could be an interrupt and exception that should take care of running in the proper context, running the RQ handle in the proper context, running pageful handle in the proper context. And there should be some unified mechanism to switch kernel page table, for instance, for PTI and KVM ASI. For the namespace private memory, there should be no need for context switch mechanism, because they will be handled implicitly with the context switch of the processes. As I said, freeing restricted page tables is kind of cumbersome. It should be integrated with existing TLB management infrastructure. It requires very special care for shared page tables, because if we share page tables at some level of the hierarchy, we can't release the page in private page in restricted page table without killing the other mapping. So everything should be done very carefully. And there should be proper counting of page tables for memory C groups and for memory allocation accounting of user processes. What we plan to do is to extend the alloc page and kmalloc with context awareness, so that memory that allocated with some special flux will be dropped from the direct map and won't be seen in other contexts. Going to suggest at some point the addition of GFP exclusive flag and slab exclusive flag for pages and slabs respectively. We are thinking about page exclusive page type, but it's a bit difficult. As I said earlier, there are very few page flags left, even on 64-bit systems. Then the private mappings will be dropped from the direct cache and returned back when the pages are freed, and all these private allocations will be allowed in the context of a process that have non-default kernel page tables. We also plan to extend the slab caches with a notion of GFP exclusive or slab exclusive in a way similar to how C groups implement the hierarchy of slabs. We are going to extend it with the private slabs as well. And then we are going to use this whole mechanism for network namespaces, and we are going to add struct page table to struct net, which represents network namespace. We do have a proof of concept of network namespace isolation, and surprisingly, we still have network traffic inside the namespaces, and that is, as it has protection of a page table for its objects. It's still not stable enough, and it looks like, well, it's I frightened myself to look at it, so it'll take some time before we post any patches about it. And putting it all together, the larger picture that we envision is that there will be page table management API for kernel page tables, and there will be private allocations both at page level, page allocator, and slab. I think vmalloc will be off. Probably we'll get to vmalloc as well. The namespaces isolation and KVM isolation will use the private allocations for their need, and the user exclusive memory with some extensions to the page cache and page table management APIs will allow secret memory areas for the user processes. So what we can conclude that using restricted contexts it reduces kernel attack surface and makes the kernel more secure. There is still an open question how much complexity and performance degradation the introduction of restricted address spaces will cause, it's not easy process to rework kernel address space management. It's a quite major challenge, and we are working on it. Thank you.